Ever just wonder what everything is, like, really made of, deep down?
It's a fundamental question, isn't it?
Yeah.
And that's where quantum field theory, QFT, comes in.
Exactly. Today we're diving into QFT. We've got some great material that honestly gives you a shortcut to understanding this really important physics.
It's the core framework, really. Our sources explain how it merges quantum mechanics, the rules for the tiny stuff, with special relativity.
Yeah.
Speed and energy, you know?
Right, and it's not just theory. QFT is the foundation for the standard model of particle physics, our best map of fundamental reality, basically.
Pretty much. So the first big mind shift with QFT.
Yeah, where does it start changing how we think?
Okay, so forget particles as just tiny balls. Think bigger. Think fields, like an electron field filling all the space, an electromagnetic field everywhere.
So, everywhere, not just where an electron is.
Exactly. The field is fundamental. It's always there.
Right.
What we call a particle, like an electron. That's just a little ripple, a vibration, an excitation in that field.
A ripple. Okay. And these ripples are quantized, right? What does that mean again?
Quantized just means they come in discrete lumps, specific amounts of energy. You can't have half a ripple, basically. You either have 1 electron's worth of excitation or 2 or none.
Got it. So particles are field ripples. How do they, interact, like electrons pushing each other away?
Well, that's the next cool part.
Well,
They interact by tossing things back and forth, other ripples. Specifically, they exchange virtual particles.
virtual, like not quite real.
Sort of. They're temporary fluctuations in another field. For electrons repelling each other, they exchange virtual photons, little flickers in the electromagnetic field. It's like playing catch, but the ball vanishes super quickly.
Messengers between the real particles.
Exactly. Force carriers. And physicists have these diagrams, Feynman diagrams. They're like little maps showing these interactions, the particles coming in, exchanging virtual ones going out.
Right, I've seen those. Little stick figures for quantum interactions.
Kind of, yeah. Visualizing the math.
Okay, fields, ripples, virtual messengers. But our sources also talked about something even stranger. Particles appearing and disappearing.
Oh, yeah. That's where Einstein's famous EMC really comes into play within QFT.
So?
Well, if you smash particles together with enough energy, pure energy, that energy can actually create new ripples, new particles. The energy literally turns into excitations in the relevant fields.
So energy becomes matter, just poof.
In a way, yeah. High-energy collisions are particle factories, and the reverse happens too. A particle and its antiparticle can meet and annihilate, turning their mass back into energy, often creating other particles like photons.
Wow, okay. And all of this whole picture leads us to the standard model.
Precisely. The standard model is basically QFT applied comprehensively. It uses this field framework to describe, well, almost everything we know about fundamental particles and forces.
Which forces does it cover? Not all of them, right?
Right. It brilliantly unites 3. Electromagnetism, the weak nuclear force that's involved in radioactive decay, and the strong nuclear force, which holds atomic nuclei together.
And the particles.
It classifies all the known fundamental building blocks. You've got quarks, which make up protons and neutrons, leptons, like electrons and neutrinos, and the force carriers, the gauge bosons, photons, gluons, W and Z bosons, plus the Higgs.
Ah, yes, the Higgs boson. Finding that was huge news. That really cemented the standard model, didn't it?
Absolutely massive confirmation. The Higgs field is the mechanism within the standard model that explains why most other fundamental particles actually have mass. Finding the Higgs particle, the ripple in that field, was crucial.
So QFT, through the standard model, is incredibly successful. But there are limitations, things it doesn't explain.
Yeah, the elephant in the room is gravity. QFT, in its current standard form, doesn't include gravity.
That's still Einstein's general relativity territory, a completely different kind of theory.
Exactly. General relativity describes gravity as curved space-time, and it's not inherently quantum. So our best theory of the very small QFT and our best theory of the very large general relativity don't quite mesh.
They don't talk to each other properly.
That's the fundamental challenge. Finding a theory of quantum gravity that unites them is, a huge goal in physics. That's where things like string theory or loop quantum gravity come in attempts to bridge that gap.
So still frontiers to explore.
Oh, definitely. QFT is amazing, incredibly accurate for what it describes, but it's not the final word. Research is pushing beyond it.
It's still mind-blowing, though, thinking that this space right here, seemingly empty, is actually buzzing with all these underlying quantum fields constantly interacting.
Absolutely. It changes your whole perception of reality, doesn't it?
Okay.
What does empty even mean if it's full of potential? full of these fields. Something to think about.